Okay, so I've been asked to say a few words about today's speaker. Gregorio Bernardi is you should already know him. He's a member of the Higgs team in the particles group of the lab, where in particular he coordinates the activities related to the future circular collider, which will be the topic we will talk about today. Gregorio has a long-standing career in particle physics. First with a thesis in 1985 on neutrino oscillations, CERN and the Brookhaven, and then on proton structure, working on proton structure functions in the H1 experiment, etc., until the end of the past millennium, let's say. And then embrace the world of collider physics, first working in the D0 experiment, where he has taken over various responsibility roles as Higgs group convener, physics coordinator, and the spokesperson of the experiment. And then more recently, he joined ATAS for the run 2 of the LHC, where he worked in particular on the observation of Higgs boson decays to BB bar quark-antiquark pairs. So for the observation of, so establishing the couplings of the Higgs boson to fermions. And in the past 3-4 years, also starting this activity on a future circular collider. In particular, is the responsible of the project in IN2P3. And now I give him the mic.
Thanks, Giovanni. Thanks, and thanks for the invitation, and thanks. It's a pleasure, of course, to give this talk in our new lab. As you know, we joined this lab with the Higgs team a couple of years ago, and we are very happy to be here. And we hope indeed there will be even more interactions because we are, of course, studying experimental physics, but to answer the big questions which are seen all over the universe, as we will see in a minute. So let me get started on this seminar. Yes, we are thinking about the future collider already now. It's a long-term project, but these things take time, and so indeed it's the moment to discuss that in detail. So I have a few points that I will address. Of course, why do we need a new accelerator after the LHC? On the linear or circular issue, I think I will leave it aside, except if you have specific questions at the end. I have a dedicated slide for that. And then I will rather concentrate on the feasibility study, what we have to do to convince the community, and talk about the potential, mainly about Higgs and Electroweak, and then see what are the next steps. So, of course, the question is, you have already such a nice LHC. Why do we need another accelerator? Why we have particle physics, which is pretty mature? The standard model looks complete. I mean, there is indeed no really outstanding point in the accelerator world at the moment, but we need to think beyond what we see in the accelerator. We have to think about what we see in the universe, and of course, in the universe there are big puzzles which are experimentally confirmed. I mean, this is the perfect lab to talk about this. Of course, there is the question of the dark matter, and this we don't know exactly, of course, what it is made about, but if it is elementary particles, it will be very well studied in colliders eventually, and we need to address this point also in this way. There is the question of matter versus antimatter, and here again, it's likely a fundamental question, which has its roots in the elementary particle worlds, but we have to study that. There is the question for the neutrino masses also, which is clearly something pretty astonishing, and it's not clear indeed if we can just apply such the Dirac scheme as we do for the other particles or not. People tend to think not. So indeed, there is way of studying things also at the collider to do these kind of things. So this is related to the fact that if this, for instance, right-handed neutrinos would be there, this could explain some of these puzzles. And so the search for these particles in a dedicated collider would be is pretty important. And of course, there is the Higgs boson. This we have discovered it like 10 years ago. And we all know that it's really special. It's a scalar particle. It's not a matter field. It's not a boson which mediates a gauge interaction, but it's a field which carries a new type of interaction. So the Yukawa type, as we will also see, that we need to study more. And now there are many proposals for new accelerators to study it and to study physics beyond the standard model. So there are linear colliders, there are circular colliders, there are photon-photon colliders, muon colliders. But we need something to really go beyond what we're doing at the moment. We need that because we don't know exactly yet the precise nature of the Higgs boson. We don't know exactly why the electroweak symmetry breaking is happening. We don't know the shape of the potential. We don't know what is the strength of this transition. What is its role just after the Big Bang? Did it play a role in inflation? We know that inflation is likely to have happened, and it's likely to have been driven by a scalar field. And it's the only scalar field we know, but we are of course wondering if there is a relation to that. And for that, we need really to determine precisely the Higgs couplings and the Higgs self-couplings. And for that, this can be studied only at accelerators. Yeah. So besides, if you want to really go beyond the standard model, there are different approaches. You can either make a direct observation of new particles, as we did for the Higgs boson, but you can also observe new phenomena like neutrino oscillations or neutral currents, and so this tell you that there is something beyond the standard model. Or you can measure deviation from very precise predictions. And so this is also important for a machine which will allow you for good precision. So the problem is that contrary to what happened in the last decades, we don't know exactly where to look for. There is not the energy scale that was available for the Higgs boson. For the Higgs boson, we knew something would happen within the TeV or so. Now we don't know if the next scale is at 10 TeV or 100 TeV or even more. And so that's why the next facility must be versatile, broad for reach as possible, because we don't know exactly where it will appear. And so the point is that I'll try to show that FCC, since it has lots of synergy and complementarities between the E plus E minus phase and the hadron phase, offers the most versatile response to these questions. So since it's a very long-term program, and since there is two phases which are clear, so the EE and the PP, and I will show more how it will really evolve later, I will mostly concentrate on the EE phase because it's the first that we want to get approved. And so we want to show, and also because initially the project was more oriented towards the PP in the sense, let's go to the highest energy and we will find maybe something new, and let's study the self-coupling, and this is sure that we can be done at HH, and that's why it was put forward. But now we realize that in fact there is also a very rich field in EE, and also it makes much more sense to first study the EE phase before the HH. That's why I will mostly concentrate on EE in this talk. So the EE, you can see very broadly, the physics program is wide. I will not go into the detail now because I will get back to it a bit more. But still, the point is that it's not only a Higgs factory. There is a Higgs factory program which is rather wide, and I will show a few slides later. But we also have different stages that you can run at a different energy. You can run at the Z energy, so at 90 GeV, you produce lots of Z, and you can see lots of type of decays and look for new physics. And this is something which will be quite interesting. So there is ultra precise electroweak program. When you look at these decays, you can study QCD, quantum chromodynamics, which also needs to be studied further. And in the decays, you can also look at the KV flavor, the C equals to BV bar or CC bar. And so you can produce a lot of these particles, a lot of taus. And so there is really a good chance to also make lots of progress in this field. And finally, last but not least, since we produce lots of statistics, you can look at feebly coupled particles. And these are important because we don't know where is the new physics if it appears through a feebly coupled particles like right-handed neutrinos. And then in that case, then it would be a possibility to observe them when you have lots of luminosity like we have in this machine. So the point is that not only FCC, there will be a beyond, so the second phase. And as I said, this is the potential which is well known and which has been studied, measurement of the Higgs self-coupling at the 3 to 5% level. Well, I remind you that this has not been observed at all at the moment. Highest reach in sensitivity for dielectric studies, dark matter searches at higher masses and more, and potential for discover heavy particles up to 20 to 40 TeV. And potential for indirect searches and also possibility to do electron-proton or heavy ion program at the highest energy. So the point is, as we are not really ready to build the HH machine, from a technical point of view and also a financial point of view, but the technical is the most crucial issue. The muon collider that you might have heard about is not as ready as it's claimed. And so the European strategy recommendation was indeed to follow the path that we are going to see. In fact, it's written here in this word, Europe should investigate with its international partners the Future Hadron Collider with a center of mass of at least 100 TeV and an electron-positron Higgs and Electroweak factory as a possible first stage. And this should be done as a global end behavior. And to do that, it has to be completed by the next strategy update in about 2026. And so that's why it has been set up, a feasibility study has been set up from 2021 to 2025, which is supposed to give answers to the important questions that you will see now. Before showing you the FCC in more details, let me compare the timeline, which is pretty impressive. Because of course you see you go from 2020 on the bottom left to 2090 on the bottom right, so it's a long span of time. Although it's not unusual, the LHC program altogether is about LEP plus LHC is about 70 years, so it's nothing crazy. But when you look in front, of course, it looks far away. The FCC program has a schedule. And you can see here with a started physics around 2048, while the LHC will stop around 2040, 2042. So small delay, small time gap between the end of LHC and the start of FCC. And this schedule is valid if the special contribution that is needed to build this machine is approved by 2020. So the special contribution, I will say a few words more later. But what is important is that still we have several years to get ready to make this approval and still to be on time to get started soon after the LHC finishes. While the other machine, ILC, which is the Japanese machine, the linear collider, the CPC, which is a circular collider, which could be built in China, or other options that I will discuss after in the US, these are really have a better start time, like 2038 or 2035, whatever. But the schedule, for instance, for the ILC, the schedule is valid only if the funding is available now, which is not the case. And we don't see how it could become available in the next few years. So to get another few years of delay is very likely, if it ever happens, because in fact, many people believe that this funding will never become available because there were many chances to get started and it didn't get started. For the Chinese collider, this is also, this was a very optimistic schedule in which case, in the case in which the Chinese would have got money in the last quinquennial plan, and this didn't happen. So, there is at least a 5 years delay on the schedule, but it's complicated and there is no obvious, there is no updated schedule for that. And recently there has been the SNOW mass process in the US, which has been exploring the different points. And on one hand, they would join the FCC if it happened. But on the other hand, they also would like to push for options which are faster. And indeed, they have options which looks like they could start before. In practice, this machine, C-cube, is a linear collider with a different type of magnet technology. And the muon collider is also, I mean, something which has been studied for many years, but which is pretty complicated to do. And for these machines, the demonstrators are yet to be realized. And so first, the demonstrators to be realized, they have to be shown to be working, and they have to be funded. I mean, the next step has to be funded. So this schedule looks very optimistic to many people. So in practice, there is a good chance, I mean, there is a chance that if the special contribution will be approved in the next years, we could have a machine soon after the LHC at CERN, and this would be great. And again, this is cost effective in the sense that you use the same tunnel to do first EE with several running, one at the Z, one producing pairs of W, one producing the Higgs via the ZH process, another one producing TT bar. And so you can really have different type of machine in a single tunnel and in a single go. And then later you replace the magnets and you go to the HH machine. And so you can really go to the highest energy frontier. So this is complementary physics, and there is also a very ambitious high field magnet program, because you need to do very high intensity magnets to get to the 100 TeV. So at the same time, there is lots of work from this side, but I will not discuss it here. And then there is the point that we are going to use common civil engineering, so the same tunnel and the technical infrastructure. And we use the CERN existing infrastructure. This is very important because, for instance, in the Chinese or in the Japanese projects, this would start from an empty field. So you would need to build a lab like CERN. CERN has been built over 50 years. It's really not straightforward to create such an organization in a few years. And finally, FCC-ee, called E, integrated, is fully integrated with the HL-LHC exploitation. It's not sharing the same tunnel, but so it can be built in parallel. So this is also pretty nice. So this is where it would be sitting, but I will show a few more things about it. Before we talk quickly about prices, this is an expensive machine, and you see on the top in the red box you have the price of the EE case, and so for the E machine you have 5.4 billion of Swiss francs for the civil engineering, so essentially for the tunnel, and another 2.2 billion for the technical infrastructure, while the machine itself, EE and injector complex, is 4 billion. So the problem, when you look at this amount, it goes down to about 11.5 or 11.6 billion of Swiss francs. And this is, I mean, that you would have to build over these 20 years, so around 2028 to 2048. And this means that the CERN budget is not sufficient to do that. CERN budget can contribute about half of it. And so there is indeed a need for additional contribution of about 5 billion. And so this is the so-called special contribution. And this special contribution will be asked probably mostly to the host countries, so France and Switzerland, because at the end of the day, this money is put to build the tunnel. And so this works. The work is done by French or Swiss companies and essentially gives work to the locals. And then you have to go to the HH part, and the HH part is also expensive, but this is also spread over many years. So then with the CERN budget, we'll probably be able to build this second step. So this is what I wanted to do. So when you hear it's too expensive, of course, you have to see that this one is not going to be taken away from other science aspects, because the special contribution will have to be directly come from the governments, because it's not something you can take out just about CNRS budget, for instance. Yeah. Yes, go ahead. Yeah.
I didn't quite understand. I thought we were using the same tunnel, but the money has to come from France and Switzerland because they're digging. I didn't understand why it's new.
Why what? Sorry.
You were saying that most of the money will come from Switzerland and France.
Yes, for the tunnel. Yes.
For the tunnel, but I thought we were reusing the old tunnel. Is there?
No. We have to build a new tunnel. No. The tunnel is 100 kilometer, a new 91 kilometer. It's a new tunnel, and the only thing we will use the LHC as an injector. Yeah, exactly.
Ah,
So this one here is the current tunnel, the HLHC, and this one, the big one, is the.
so the reuse is really just the administrative infrastructure.
Yes, and also, of course, also the tunnel of the LHC, because this will be used to inject you need to do several rays in energy, and so you need such a
I assume that's a smaller.
yeah, it's a 27 kilometer instead of 91. But the let's say, for instance, when we do such an aspect, there is lots of legal point when you try to, and so you need the services which are able to do that. And so this CERN has developed that over the years, just to take an example. Okay, so, okay, yes, in fact, this was, I went to the next slide, which is fine, which is the collider. So let's go to the feasibility study, just to show you that this is based on 5 big pillars on the physics. Let me see if I can find that. Physics and experiments, which I will essentially, that's where we work as physicists. But of course, there is accelerator physicist, and then there is technical coordination, host-state processes, and civil engineering, and the financing model, which is, of course, not negligible in such an aspect. If I zoom on the physics and experiments, this is set up in, okay, there is here the interaction with the machine. Then there is physics software, physics program, physics performance, detector concept. And if you zoom on the physics program and physics performance, you see that you are organized like a big collaboration with a physics group like Precision, Electroweak, Higgs, stuff, flavors, QCD, and beyond the standard model. And so this thing is set up, it's working. There are people working in all these groups, and we are responsible, and we are attracting as many people as we can, because this project is a global one. And so eventually, most of high energy physicists could work in this aspect, because it covers all the fields of high energy physics. So let's go back to the plan, to the FCC run plan. And as I said, this machine can run up to about 360 GeV. Then you cannot run beyond, because you have so much synchrotron radiation that it costs too much, and you cannot run beyond that. But with that, you can do lots of physics. You can run at 90 GeV, and then sit on the Z resonance. You can go at the WW thresholds, where produce lots of Ws. You can do at the ZH threshold, and so there you will produce lots of Higgs, or you can go at the TT bar production resonance, and you will produce lots of tops. And this, you can see here, you see that the run duration is in fact rather short. So you can do this physics program, which is huge, in a really relatively short amount of time. When you see that LHC now is running since 2010 and will go to 2042, so it's about 30 years. And here you see in 15 years, you can do four different aspects of physics so it's faster, and you will have lots of physics coming out of it rather soon. And in fact, there is even possibility to do a run at the Higgs pole, so at 125 GeV. So you just do E plus E minus 18.1 Higgs at 125 GeV. And if you see decays with enough statistics, you could try to look at the E plus E minus decay and look at the Yukawa coupling of the Higgs to electrons, which is not doable anywhere else as far as everybody sees at the moment. Okay, let's just small thing to see. To show that this thing is progressing. The overall layout and placement optimization across both phases is done in a way to be sure that we can avoid, reduce, compensate the damage to the nature around. There is constraints such this civil engineering, technical feasibility, which have to be respected, territorial constraints, the nature accessibility, technical infrastructure and resource needs and constraints, and some economic factors which have to be taken into account. And so many, like we have studied, they have studied about 200 placements. And at the end, there has been a overall review last year, and the review has converged. And the idea was to choose the lowest 8-point options. Before there were 12 points like that. And when you do that, it's very nice because it means that you can have 4 interaction points. So it means you can have 4 detectors and you can have 4 experiments like at LEP at that time. And so this multiplies by 4 your statistics, and you can also have complementary detectors. And so this is pretty important for the physics. And so this is progressing. So this is nice. This is concrete. And the next step, once we will have the accelerator, will have to be the detectors. And so this is the work in which the physicists, energy physics are involved. They are studying what are the requirements for these new detectors. And these requirements depend on the physics program. So for the Higgs factory program, for instance, we know that we will need very good momentum resolution at the level of 2⁻⁵ by GeV for the sigma pt or pt square, because we need to measure the muons precisely for the Higgs physics. We have also constraint on the jet energy resolution and so on and so forth. But this is one set of constraints. But then we have also this very precise Electroweak program, and this will give you another set of constraints. So when we will put together the constraints that you have from every physics group program, then you will see, then we will end up with the different detectors that you can build. And out of 4 detectors, you could have one which is more specialized towards Higgs and Electroweak, while another one could be more specialized towards a flavor, or another one could be more specialized towards the search of decoupled particles. So this is what is being done in these years during this feasibility study, and it's rather interesting, of course, and it's something which has to be requires lots of thinking and not to make a mistake, because this impacts the potential, the physics potential of the project. And for instance, this I will just show you some detectors which are in the study. One which is called the CLD, because this was a detector which was coming from CLIC. There was a CLIC design. CLIC was another type of linear accelerator which was developed at CERN in the last decade or so. And this was based on a full silicon tracker and a high granular silicon tungsten electromagnetic calorimeter. And this was one of the detector which is possible. Another one has been proposed more recently, in particular by the Italian community, but also with Americans and so on. And this is based on a very light drift chamber for the tracking. And then there is a dual readout calorimeter, which is a calorimeter which allows compensation, because it allows to measure at the same time electromagnetic and hadronic response in the same go. And more recently, France has been very interested in liquid argon calorimeter, or liquid argon or liquid krypton. So this is so-called noble liquid decal, and in fact in the lab we are going to work on this one as well. And there is lots of experience in such a calorimeter. For instance, the Atlas calorimeter is a liquid argon calorimeter. And the difference is that this calorimeter has to be very fine grained, because we want to do precise physics. And so we want to have the size of the cell should be rather small to be able to distinguish the physics that we want to do. But there are other options also with crystal calorimetry. This is active in the US and in Italy. And there are other options. And so there is work going on here to design detectors, which will be presented at the end of this feasibility study, and showing that indeed we can do the physics that we want to do. So turning now to the physics, I will describe a bit what we can do on the Higgs boson at FCC-ee. The baseline is that we will have 2 interaction points. So if you have 4 interaction points, you get essentially twice the events. And so this increases the statistics, the precision, but the bottom line is here. And normally we will collect about 1.2 million of Z Higgs events, and about 100,000 events in which the production of the Higgs goes from WW fusion, as I will show you the graph in the next slide. And so there are three types, let's say we can separate the measurements into three big types. One which are statistically limited, like typically the Higgs couplings to fermion and bosons. At E plus E minus, you can do very precise measurements, model independent, but you will still be limited by statistics for many of these measurements. However, what is really nice is that with these measurements, we will have finally an absolute normalization, which is not the case at LHC, because at LHC you collide partons. I mean, you collide protons to protons, but you don't know the incident energy exactly. So this will be a very good progress. But you will have also measurements like the Higgs properties, CP violation, or the Higgs weight, the Higgs mass. This will also be statistically limited. We will try to get closer to discovery level with the Higgs self-coupling. I will show a bit more later. And we will try to do, as I said, measure the Higgs to electron coupling in the S channel. And again, I'll show a slide on that. So this is the production at FCC-ee as a function of the square root of S. So you see that the threshold is more at 255 to 60, but we will run at 240 because to optimize signal over background. And the graphs that you see, so we are dominated by E plus E minus 2ZH. But when you go to higher energy here, you start to have this other graph, E plus E minus, in which you have a WW fusion and the Higgs is produced with two neutrinos that you don't see, of course, in the fourth region. And this is very different from what we were seeing from what we were studying at LHC, in which the incoming particles are gluons or quarks, and so it's another way of doing that. And so at the end, we don't have so many events compared to LHC. At LHC, there are more events, in fact, but there is much less background. There is essentially no background, and that's why we can really do precision physics. And since we know also the initial state, yes.
What can you remind me why the Higgs
Higgs
double Higgs in that graph?
In that, well, we don't have the center of mass energy.
What is the maximum? I thought you said 100.
360.
And then you can have two Higgs. Right.
No, well.
Coupling is negative or something.
Just wait a second. Why don't you get with E plus E minus couples? Well, E plus E minus couples to Higgs is very negligible, yeah. So you cannot go through this graph. At the Z, yeah, and then you have Z to HH. Sorry?
You are, I mean, yeah, Z plus 2X, it's 340 GeV, right? So it's there. If you want to do Z plus 2X, right?
No, you would like to have two Higgs. You would like to have two Higgs, and then you have 250.
The Z is virtual. In virtual Z, probably it is suppressed. Right? It's very far from the Z pole, probably.
Okay. Well, Z to X6, I mean, X to Z, the branching ratio is rather small. It's what, 10%, 5. The branching ratio to X to Z is 5%. So you have another factor 10, you lose another factor 10 or 20, and you cannot produce it to HH. Well, yeah, it's a matter of. Yeah, we can give it. It's a good. It's an obvious question that you're not able to answer. That's not so nice, but okay. Okay. So what we can say, however, is that since we know the E plus E minus initial state, you can reconstruct this system just by kinematic constraint, by looking at the Z and knowing the E plus E minus. This is the formula mx of this recoil place. And so this doesn't, you don't need to know what happens in the Higgs system. And if you plot this recoil mass, you see that indeed you have a peak here of the Higgs, which has the width of a few MeV. And this means that if the Higgs decays in an exotic particle, you will see it. You will see it in the number of events. You will not see the exotic decay necessarily. If it's invisible particles, you wouldn't see them, but you would see that the peak would be higher than what is expected from the standard model. And so this is a big advantage to be able to look at invisible decays of the Higgs, because if there are new physics, it could be hidden there. And this is not possible at LHC, because at LHC you don't have such a constraint. You don't know what is the initial energy of the gluons, because they carry a fraction of the proton energy, and on event by event it changes on every event. So this will be a big plus. And at the end of the day, the precision that we will be able to go, we will be able to go what we expect at the end of HL-LHC on these coupling parameters. The precision will typically between 1–2%, and at FCC-ee we will rather be talking about between 0.2 to 0.7%. So you will gain almost a factor of 10, and again we hope to see deviations which would tell us that indeed the standard model is not fully correct at such a level of precision. And this precision here on the right can even be improved if you have 4 detectors by about 30%. Note that if you go and look for rare processes like Higgs to mu or Higgs to gamma gamma, there the statistics is still the dominating part, and there the hadron colliders, which produce much more Higgs than the E plus E minus, will still win. But we can combine, of course, the two aspects, and get the best Higgs. Finally, to finish on the Higgs, so I mean not exactly the two points. One is the Yukawa coupling, as I was mentioning. So this the Higgs decaying to EE, given the mass of the electron, this branching ratio is very tiny. It's at the level of 10 to the minus 9, and means that if you try to produce a Higgs from E plus E minus, the cross section is very tiny, 1.64 femtobar. And so if you are able, however, to put yourself very precisely at 125 GeV at the mass of the Higgs, that you need to know precisely at the MeV level, then you can produce enough events to be able to see this production. And eventually we could see the Yukawa coupling here at the level of the standard model. So this is what we would expect. And this is the best you can do also at the moment. You need something like close to 100 times the standard model. So it's really a very big improvement. And this would show that the Higgs mechanism would also hold on the first generation, that we know only from a theoretical point of view, but we have absolutely no clue from the experimental side if it's true. At the moment at LHC, we have seen, well, the third generation, the B's, the taus, this we know they corresponds to the Higgs Yukawa, to the standard model. At the second generation, we start to see the mu, we have some hints, but it's not yet there. And the first generation is very far away. It will not be seen at LHC for sure. And finally, to conclude on the Higgs self-coupling. So the Higgs self-coupling, as we know, is determining at the end the potential, the shape of the potential, the so-called Mexican hat. This is what we have in the standard model, but we don't know if it's like that. This is what the standard model predicts, but we have no experimental verification of this thing. And so the most direct way of doing it would be to look directly at the production of two Higgs through this graph at hadron colliders, for instance, or at lepton colliders. You could do it this way. Although these are not, it's not all fully direct, because there are also always graphs which interfere, which do not carry this triple vertex. So it's not fully direct, but it's more direct than what we call indirect. Indirect is really looking at the radiative corrections. And the radiative corrections, if you have a different, if you make the measurements at different beam energies, like you see here, you go from 240 to 360, which is the TT bar. You see that one cross section, this one, the ZH, and the one which goes through the nu bar, don't have the same dependence. And from this dependence, you can then make constraints on the delta kappa lambda and on the coupling to the Z. And so with accumulating different running points, you can get more precise. In fact, so the current study shows that from this global fit, you can have a precision with 4 interaction points at the level of 21%. And 20% sensitivity means the 5 sigma observation of such a coupling. And so this would mean that we would be able to observe self-coupling of the Higgs before HH would produce it and would measure it much more precisely. And again, let me remind you that at the end of HLHC, for the moment, we hope on a 50% sensitivity, so which is about a 2 sigma sensitivity. So even if we progress, and we probably progress a bit, but we will not get to observation at HLHC. So this will be another big, very big step forward. Just to show you on this point, this is the yellow things at FCC-HH, then you will be able to measure it down to 3.8% as far as you can see at the moment. And so the combination of the measurements of HH and EE at the end will give us the optimal knowledge of the couplings of the triple Higgs, the coupling, the gamma-gamma, and the Z-gamma, and so on. And so at the end of all this, I mean, we really hope to have a very clear picture of the Higgs. So let me go a bit faster on the rest of the program, although it's very interesting. Probably we would need a dedicated talk for that. So at the Z peak, we will have what we call the TerraZ program. So the TerraZ, why? Simply because when you look at the cross section and the luminosity that we expect, we will be producing more than 10 to the 12 events per experiments. So this is 100,000 times the lab statistics. So it's really a huge number, a huge progress. And here again, we hope to see something which breaks down in the standard model with such a jump in precision. And for the Electroweak program, we also here, we will run 2 years at the WW threshold. And here again, this has been done at the lab, but this will be again 2,000 times higher lab statistics. So again, very big progress on this aspect. And when you put this Electroweak precision observable that we will be able to measure here, it's a long list on the left. I will not go through them, of course, because it's a lack of time. But we see that, for instance, the precision that we were having before, let's see on MZ, before it was 2.2 here, MeV. Oh, sorry, this is this is 4 MeV, so yes, 2.2 kV. No, whatever. 91.2. So the systematic, which we will reach, will be 100 MeV, while the statistic will be 4 MeV. And so this means that at the moment we are challenged by the systematics compared to what we are able to do with the statistics. However, we also know that at lab, basically we were able to match the precision of the statistics and the systematics, because when you have more statistics, you can do indeed the systematic studies, which allow you to reduce at least all the systematic coming from the experimental aspect. And so there is lots of work going on in the Electroweak group to reduce the systematics and see again that we will be able to make this big progress on this thing. Now there is a crucial aspect, which is the theory errors there, and the theory errors are being worked by theory groups. I mean, there is a network of theorists around FCC, which are working towards improving the precision of these errors. The other aspects of the TerraZ, so is I mentioned before, the heavy flavor and the tau factory and the QCD, to go beyond what will be done as Super KB at Bell 2 and the upgrade of LHCb requires something like 10 to 11 B pairs, and FCC-ee will provide another order of magnitude above. And typically, this is the projection that for you have on some CKM matrix element. We will go from this precision on the angle gamma from 0.025 to 0.004, so rather significant improvement, factor 6 here. And also on the VUB precision here, just to take as example, from 2.5% down to 1%. So this will again push forward the knowledge of the CKM matrix element, but we also look for Fibonacci neutral currents, CP evaluation mixing, study other rare penguin decays, and as there are anomalies in the B sectors, this can be studied also more precisely with such statistics. And for the lepton universality, this will be able to be tested with the tau decays, which will also be huge. Again, we will gain another order of magnitude compared to what we have now. And for that, we will probably need special detectors on particle identification, which are understanding. To conclude on this Terra Z, we will also have lots of hadronic Z decays, and this allows really precise input for QCD studies, and we will gain another order of magnitude precision on alpha S and C's coupling, since we will be measuring, it's running, since we will be measuring it at different values of the square root of S. One slide very quickly on the fact that we also have a top factory. Again, we will be able to scan the region from 340 to 360. And so it's exactly the place where there is a threshold. And so by measuring this shape, you will be able to measure the top mass and the top width with very high precision at the level of 17 MeV and 45 MeV. And this, I remind you that in hadron colliders, this is a very difficult, not only a difficult measurements, which is much less precise, the level of, we hope to get below 100 MeV, but which is also not very well defined from the theoretical point of view between the pole mass and the mass which is obtained in the QCD calculations. So let me come to the last point, feebly interacting particles. So we mentioned that. We have the puzzles that we mentioned at the beginning, and this could be these exotic particles like dark photons or axon-like particles, sterile neutrinos. They are all feebly coupled, and so with the high statistics that this machine will have, we will be able to push push the limits on the couplings that you have between the heavy neutral particle and the standard model particles. And definitely, this is the improvement that FCC-ee will allow just by looking at potential decays of these particles, or through the mixing with other particles. So the gain will also be big. And here again, we hope to be able to see something new. So the summary of this discovery potential and the highlights of this machine is that it could, at the same time, it will explore the 10 to 100 MeV energy scale and beyond with precision measurements. I didn't really connect the precision with the energy scale, but typically we will be studying this range. And this is an improved precision on many electroweak quantities between 20 and 100 times. There will be very high precision measurements of the standard model parameters, essentially of all the standard model parameters. We will get into model independent Higgs measurements, so we'll constrain the Higgs very more precisely. We hope to see the Higgs self-coupling. We hope to see potentially a violation of Flabault conservation or FCNC phenomena. Of course, we hope to discover dark matter if it's in the right range. We explore really new ground or new weakly coupled particles. And there are also other opportunities in QCD or in heavy flavor. So there is, the point is that FCC is not only a Higgs factory, but it really addresses all the physics of the standard model. And so any place where it could be breaking down, it will be explored by such a machine. So our main goals until 2025 is we need to do all the steps to enable a project decision by 2025, 2026, which is the next European strategy update, in order to be able to start building the tunnel around 2028 or 2029. So there are 4 points here that I will not describe because these are a bit beyond our purview. I mean, this is really the way be financing this thing, how we prepare the administrative processes with the host states and the site investigations which are going on and so on. But for us, we have also lots of progress. We need to continue the machine design and the main technology R&D lines. We need to complete the first physics case studies to be able to know what are exactly the detector requirements and come up with some proposal, concrete proposal of detectors to show that we can really use this machine. We need to establish user communities and start to work towards proto collaborations. And the important point is that the LHC community, which are thousands of people, you know, there are 3,000 people on CMS, 3,000 Atlas, and if you have 1,000 on LHC analysis, will have to bring enormously to the project by contributing to this R&D detector and to reinforce the physics program that I just described briefly before. So at the end of the day, if you look at this yellow box, I mean, thanks to synergy and complementarities, we believe that this machine offers the best approach to today's physics landscape, and it can be constructed while accomplishing the HL-LHC program, which is of course crucial because we have invested a lot in this machine, and we still hope to make discoveries before the end of the run. There are many opportunities that we have talked about. We hope that more people will join, and so this is a publicity to everybody can really help. I mean, phenomenology or just in yourself. And we have some joint France-Italy workshop, which is going to come up soon, in which everybody is welcome to see and see what are the progress. Okay, thank you.
Thank you very much. Questions? Yes.
What is the main challenges for detectors now? Energy goes up by 3, let's say, for electrons, and by 10 for hadrons.
Yeah.
The new detectors, what are the big things that are difficult to do?
I'm not sure. You talk between E.
Between the LHC and
Yeah. No, that's the point. Yeah, the detector. So again, we are going to have detectors specialized for the E machine and different detectors for the HH machine. So it will not be the same. Yeah? There will be 4 collaborators. I mean, we hope to have 4 detectors for EE, and these are the more or less the design that on which you're working. And this looks, I would say, doable at first view, because what it will be, while the HH will be very challenging because there is a very huge pileup. I mean, like LHC, but another order of magnitude higher. So, but this is coming later, and there is.
And then, okay, I found nowhere a coupling of 2X to Z, so probably it does not exist. I have to look here again. I have another last question. Well, maybe we should ask it for now. Is there any idea to look for dark energy?
Yeah, no, that's a good point, because it's one of the small questions around. Yeah. No, unfortunately, no, there is no ideas at the moment for this.
If dark energy is a scalar, one of the possibilities, it can be a scalar.
Yes.
Like for inflation, which is one possibility. Then anybody has thought about looking for these scalars?
No, I mean, beyond the fact that we are looking for this LLP, I mean, if it's a feebly interacting particle, again, it might appear in such a. But I think it's. I think you raise an important point. Many people say, okay, why do we need these machines and so on? It's true that there is, I mean, are rather expensive and so on. On another hand, it's indeed, if you have some strange, I mean, like say, for the dark matter, it's easier to imagine. For the dark matter, it's easy to imagine a particle there, and then you will see it in such. Until you see it in an accelerator, it will be difficult to believe it completely. And for the dark energy, we need more input, more experimental input from the cosmos. Yeah. Yes.
I just had a couple of operational questions. One, how much energy does this use? And 2, is the computing, since we're starting to use computing FCC, for example, is the computing model the same for the FCC as for CERN now?
Two things. So in terms of energy, the energy consumption is similar to what is going on with the LHC at the moment. So it's
not going up.
no, it's not going up a factor 10. And in fact, yeah,
That's about a megawatt or something?
no, it's well about half of it, yeah. Half of it, yeah. And the question is still the best machine, even for instance compared to the linear collider, since in terms of energy per Higgs boson produced, it's much better because we have such higher statistics. So this is an important argument when people start to talk about with the greenest and so on. So this is definitely the cheapest way in terms of energy per Higgs boson to produce such physics. Yeah. And the second point was
the computing model.
and the
It's
computing.
very different from what we do in cosmology.
Exactly, the computing model. So I mean, of course, you have lots of experience with the LHC computing model, and at this stage, I mean. There is much less background in those events. So the concentration of good events is higher in such a machine. So at the end, we will treat lower levels, I mean, lower amounts of data. So let's say the computing model that we have for LHC should be sufficient for FCC. For FCC-HH, then it's another thing, because of course there we go up compared to LHC, and we will have to improve the thing. But okay, there is progress, fortunately, on the computing aspects.
I have a curiosity question. So when you exactly on this point, so when you make like plans for the next 50 years, basically, so how do you I mean, are you using like current state-of-the-art technology, or like, because for example, for the computing thing, but there use the informatics in 30 years.
Yeah, no, there is extrapolation all the time. I mean, basics on Moore's law. I mean,
so even like the budget takes into account extrapolation of expected technology advancement, or
no, for the detectors, no, it's not as extrapolated as for computing. Yeah, no, for the detectors. For computing power, yes. I mean, I think there is some extra. I'm not a specialist, but I mean, I mean, we are not counting that we will have the same computing power today, and so this we know that this will improve. But no, otherwise the budgets themselves are built on technical options, really technical. I mean, these 11 billions are documenting on what we could do today. Yeah. Yes.
So actually, it's related to Matthew's questions about the magnets. You mentioned that there is going to be some R&D program for the magnets. So are you still like looking for, like, you still need a technological breakthrough to reach the like desired characteristics, or do you have a path forward?
So it's not exactly a breakthrough, not like in, for instance, in the muon collider, you still need a breakthrough probably to get there. But for these magnets, we have not reached, I mean, we need to do 16 Tesla magnets and be able to build them at an acceptable cost. And so technically we are close. I mean, we are able to do 14 Tesla magnets, so we are 14 to 16 is not that far. We know that we can still, so we need to progress a bit on energy, and we need to be able to build them in a sustainable way. I mean, it has to be affordable. So let's say the FCC machine, this we know exactly how to build it today. So this is really nice. That's why if we would be approved, then we could get started. The FCC-HH, we could not easily approve it today, because there would still be the little chance that we would take a lot of delay because we don't manage to set up the process, the industrial process to build all these magnets. But in the coming 15 years or so, we hope to be there. But indeed, it could. But okay, this will be discussed in about 10, 15 years. And indeed, if you have not reached that level, probably it will delay the decision for the next step. But the main point here is to see that already with this step, this E step, we will learn a lot. I mean, potentially we can make discoveries which are breakthrough and so on. So, and will tell us even if it's sensible to make physics at 100 TeV. I mean, maybe we'll see deviations showing that indeed we can really have discoveries there, direct discoveries.
Okay, so just to confirm, for the FCC-ee, the technology is ready.
Yeah, it's built on lots of, there are lots of E plus E minus collider which have been, and so putting together the different pieces, we know that we can reach this luminosity. Yeah.
other questions? Okay, so if not, let's end the
Okay,
speaker.
thank you.
We have coffee and biscuits.